So I want you to imagine, just for a second, trying to explain how to tie a shoelace to someone who has never, ever done it before.
Oh, man, that sounds like a nightmare.
Right. It is. But there's a massive catch here. You are only allowed to use words. You can't use your hands. You can't, like, point to anything. And you have zero visual aids.
So you are entirely restricted to pure text.
Exactly.
Yeah, you'd find yourself saying these ridiculous things like, form a bite with the standing part of the lace, wrap the working end around the bite, and, pull through the aperture.
Pull through the aperture. Right. It sounds less like a helpful instruction and more like, I don't know, a nautical engineering manual or something.
It really does.
And it is incredibly frustrating for both people involved, mostly because you quickly realize that some concepts simply defy pure verbal description. I mean, you just had to see the spatial relationship, right?
Yeah, you have to actually witness the overlapping physics of the knot.
Exactly. And that frustration brings us directly to the mission of today's deep dive. We are jumping into this fascinating new research paper titled Einstein World Models.
Yeah.
And the researchers here are basically trying to figure out how to give large language models the ability to perform visual thought experiments.
Which is a huge deal. They basically want to give AI an imagination.
Yes. And honestly, this feels like a massive shortcut to being totally well-informed on the absolute state-of-the-art in generative AI right now, because the stakes here are quite high, wouldn't you say?
Oh, absolutely. I mean, we are looking at a fundamental inquiry into the limits of language itself. So to give you some context, right now, the dominant paradigm for how AI reasons through complex problems is known as chain of thought, or CANT.
Right, which we see all the time now.
Yeah, when you ask a model a difficult math question or a logic puzzle, it often, outputs its step-by-step logic before actually giving you the final answer.
It shows its work, basically.
Exactly. And under the hood, it is generating tokens, which are just fragments of words, one by one. It's a process called autoregression.
And we know that large language models and they're incredibly adept at manipulating those symbols. They can write complex Python code or synthesize historical documents purely through that text generation.
They are brilliant with symbols and words, yes.
But the paper argues that this chain of thought approach, it hits a hard brick wall the very moment physical intuition is required.
It really does. Because when a problem hinges on physical variables, things like object identity or containment, contact, motion, material states, a text trace is an incredibly inefficient way to represent those realities.
Wait, inefficient how?
Well, in a text transformer, spatial coordinates have no intrinsic physical relationship to one another. So the model might track the words, the ball is in the cup, right?
Sure.
But it has no spatial anchoring for what in actually dictates about the physical boundaries of those objects. It just knows those words frequently appear near each other in its training data.
So if we rely solely on text for physical reasoning, it's a bit like trying to navigate the complex, winding streets of a brand new city by reading a massive, scrolling spreadsheet of raw latitude and longitude coordinates.
That is a perfect analogy, yes.
Like, you might technically have all the data, but without a map to visually organize it, you're going to get totally lost.
Because the temporal and spatial realities are simply stripped away when they get compressed into raw language data.
Okay, I'd have to push back a bit on the novelty of this, though. Because, we have vision language models everywhere now.
You do, yeah.
Like, I can literally open an app, snap a photo of the inside of my refrigerator, and the AI will analyze the image and tell me, I can make a surprisingly decent frittata out of what's in there. So if AI can already see, why do we need this whole new framework for visual reasoning?
That's a great question. The distinction lies in where the visual information actually originates.
Okay, what do you mean?
With vision language models, or VLMs, the visual data is provided externally. You took the picture of the fridge. The model is just reacting to a static, predefined input that you handed to it.
Oh, I see.
But what happens if the AI encounters a conceptual problem where the visual scenario hasn't been drawn yet? Traditional VLMs are reactive to the pixels you feed them. They do not generate the hypothetical visual scenarios required to actually solve a text-based problem.
So they can describe what is, but they can't imagine what could be.
Precisely. And to solve that specific gap, the researchers behind this paper actually looked back at how human beings overcome the limitations of language.
Right, which brings us to the name of the paper. They heavily reference Albert Einstein, which is obviously where the Einstein world model's name comes from.
Yeah, his autobiographical notes actually provide this amazing window into cognitive problem solving.
The famous anecdote is the thought experiment that helped him develop the theory of special relativity, right?
That's the one.
So for you listening, Einstein basically pictured himself standing near the burned clock tower, watching a beam of light moving away from him. And he asked himself a very specific question.
A very weird question for the time.
Yeah. He thought, if he could somehow accelerate his own body until he matched the exact speed of that light beam, would he look over and see the light wave frozen in place?
Which is such a profound question because according to Maxwell's equations regarding electrodynamics at the time, well, a stationary oscillating light wave was empirically impossible.
The math literally did not allow for it.
Right. It broke the math.
Yet Einstein didn't solve that tension by just, crunching more equations on a chalkboard.
Yep.
He visualized it. He transformed a highly abstract mathematical paradox into a concrete temporal scene in his mind.
He built a simulator in his head.
Exactly. And later in life, when asked how he thought, Einstein explicitly stated that words had to be sought for laboriously, only in a secondary stage.
The core elements of his thought were visual and muscular.
The text was the afterthought.
And that completely inverts how AI operates today, where words are the primary and often only mechanism for thought. And this is the genesis of the Einstein World Model Architecture, or EWM.
Okay, so EWM. Let's get into the architecture. The E serves a dual purpose here, right?
It does. It stands for Einstein, honoring his reliance on visualization, but it also stands for externalized.
The externalization part is what I find conceptually difficult, honestly. How exactly does a text-based AI externalize a visual thought process?
So the architecture works kind of like this. When an EWM-equipped AI encounters a complex physical reasoning problem, it begins deliberating using standard text generation. It starts its chain of thought.
Generating tokens.
Right. However, when it realizes it lacks the physical intuition to proceed, it actually pauses the text generation.
It just stops talking.
It stops. It writes out a specific query and calls upon an external world module, which, you can think of as a generative video renderer.
Okay.
This module takes the AI's query and creates a short visual-temporal rollout, basically a short video clip of the scenario.
Wait, I want to clarify something here just for our listeners, because world models is a massive buzzword that gets thrown around a lot right now in Gen AI. I read about systems like VLJPay recently. Are EWMs doing the same thing?
They are fundamentally different, and the distinction is really critical. So VLJPay, which stands for Video Joint Embedding Predictive Architecture, it's designed to learn predictive representations.
So it's predicting the future of a video.
Essentially, yes. It watches a video where certain portions are masked out, and it predicts the missing information in an abstract embedding space. It is a fantastic predictive simulator.
Like for robotics, right?
Exactly. It's often used for embodied agents, so like a robot trying to predict what a room will look like if it takes a step forward. But EWM is a reasoning system. The AI isn't navigating a physical environment.
Right, it's just trying to solve a text prompt.
Yes. It is generating the video solely as an inspectable hypothesis to help it figure out the answer, just like a human imagining a scenario.
Okay, but I'm still hung up on the actual mechanics of this. An LLM is a text engine. It processes text tokens. So if it pauses its text output, asks for a video, and the world module generates an MP4 file, how does a text engine watch a video?
Well, it all comes down to tokenization. You have to remember that a visual token is fundamentally just a mathematical vector, much like a text token is.
Okay, so it's all just numbers at the end of the day.
Exactly. In this architecture, the generated video frames are chopped into a grid of patches by a visual encoder, often a vision transformer.
So it slices the video up.
Slices it up, and these patches are compressed into high-dimensional vectors, visual tokens. So the LLM doesn't see an MP4 like you or I would on YouTube.
Right.
It ingests this sequence of visual vectors directly into its context window, processes them right alongside the text vectors, and extracts the spatial and temporal relationships.
Oh, wow. So it's translating the video back into a mathematical language that the AI can just seamlessly weave into its existing text logic.
You've got it.
It's somewhat like if you and I were trying to plan a complex road trip entirely over a phone call, and we kept getting confused about the overlapping highway routes.
Because trying to explain a map out loud is terrible.
Terrible. Eventually, I asked you to quickly sketch a map on a napkin and text me a photo of it. We both look at the napkin. We realize the bridge we wanted to take is actually 50 miles out of the way, and we revise our plan based on the visual.
That's a great way to think about it. The visual rollout externalizes the latent assumptions. It forces the AI's internal hidden logic out into the open as a public, inspectable reasoning component.
Inspectable hypothesis. I love that term.
And this introduces a really crucial concept from the paper, actually. The idea of faithfulness.
Right, because if I draw a map on a napkin, the scale is going to be completely wrong. I mean, it isn't a geographically true representation of the state.
Nor does it need to be, and that's the beauty of it. The generated video in an EWM does not need to be physically flawless to be highly useful.
Oh, really?
Think back to Einstein. His thought experiment of catching a light beam was physically impossible. You cannot accelerate a human body with math to the speed of light.
Right. The truth of the scenario was technically false.
It was entirely false, but the visualization was faithful to the abstract tension he was trying to resolve. It made the variables concrete enough for his brain to actually reason about.
That makes so much sense. If we only look at traditional text chain of thought, an unfaithful trace is a massive problem.
Yeah, it's a hallucination.
Right. And AI might output this highly confident, logical-sounding paragraph that completely masks the fact that it hallucinated the physical dimensions of the objects involved.
Yeah.
But by forcing the AI to render the scene into a video, those hidden spatial hallucinations become totally public.
They become public, and they can be inspected. And if they can be inspected, they can be debated.
Debated?
By who?
By the AI itself. The paper outlines a theoretical extension of this called ensembling, which is where this architecture becomes incredibly robust.
Ensembling. Okay, that sounds like it involves multiple models. How does a debate between algorithms actually work in this context?
So instead of relying on a single world module to generate the napkin sketch, the reasoning AI could query multiple distinct world modules at the same time.
Oh, wow.
Imagine one module is heavily biased towards strict Newtonian physics, while another is tuned for creative, hyper-realistic rendering. They each generate a competing visual hypothesis for the exact same problem.
So the text reasoner gets handed two completely different videos of the same scenario and basically has to figure out which one makes more sense.
Precisely. The language model evaluates the competing sequences of visual tokens. The disagreement between the rendered rollouts highlights exactly where the physical ambiguity lies in the prompt.
That is wild.
Yeah. By cross-referencing these visual hypotheses against his own text logic, the AI can filter out the physical inconsistencies and arrive at a much more grounded conclusion. Okay, I have to stop you there, though. Because while that sounds incredibly powerful for problem solving, the computational overhead of that seems entirely unscalable.
Oh, it's massive.
I mean, we are talking about rendering multiple high-fidelity videos mid-thought. You cannot have an AI spinning up a whole server farm to generate a Pixar-level short film just because you asked it a basic math question.
You're absolutely right. The resource cost would bankrupt any deployment immediately, which means the system must learn restraint.
You have to know when to use the tool.
Exactly. So the researchers propose a specific two-stage training pipeline to teach the AI not just how to use this visual tool, but when it is actually necessary.
Okay, let's break down that training. The first stage mentioned is supervised fine-tuning, or SFT. Now, my understanding of SFT is that we are essentially handing the AI a dictionary and a grammar guide, right?
That's a good way to put it.
We are showing it the specific syntax required to output a think tag, make the tool call for the video, and format the final answer.
You are establishing the vocabulary, yes. But SFT is also demonstrating the behavioral trace. You provide the model with examples of perfect reasoning paths.
Okay.
And crucially, this training data includes prompts where the AI deliberately does not call the world module.
Ah, so it learns the interface, but it also sees examples where pure text reasoning is totally sufficient.
Exactly. It learns that it doesn't need a video to solve 2 + 2.
But SFT alone doesn't guarantee the AI will make the most efficient choice when it encounters a brand new unseen problem, does it? It just knows the rules of the road.
Right. It knows how to drive, but it doesn't know the best route yet, which necessitates the second stage, reinforcement learning.
The famous RL step.
Yes, and the researchers suggest using a protocol like GRPO or Group Relative Policy Optimization. This is the mechanism for teaching the model selectivity through a carefully balanced reward system.
Okay, GRPO. How exactly does a group relative reward system change the AI's behavior in practice?
So in GRPO, when the AI is given a prompt, the system doesn't just generate one single answer and score it. It actually generates a group of different reasoning paths, say 8 different attempts at solving the exact same problem.
Okay, so it throws 8 darts at the board.
Right. The system then calculates the average success of that specific group of 8.
Oh, so it's grading on a curve against its own variation.
Exactly. But here is the kicker. The reward isn't just about getting the final answer correct. The researchers introduce a call budget penalty.
A call budget penalty, meaning it gets penalized for asking for too many videos.
Yes. Let's say Path A uses the world module 5 times to solve a simple arithmetic problem and gets the right answer. But Path B uses 0 world module calls, relies purely on text, and also gets the right answer.
Okay, I see where this is going.
Path A will incur a massive budget penalty, which drops its relative advantage score way below the group average. So the AI automatically adjusts its internal policy to favor the highly efficient Path B.
It's learning to optimize its cognitive load. It reminds me of like a student working on a science fair project about volcanoes.
Okay, sure.
You have to teach the student when it is actually necessary to spend 3 whole weeks building a papier-mâché model that erupts baking soda versus when they can just draw a diagram on poster board and convey the exact same information.
That is spot on. The EWM learns to weigh the cognitive payoff of the visual thought experiment against the compute cost of actually rendering it.
And in theory, that balance creates an incredibly efficient, physically intuitive AI.
In theory, yes.
But in practice, the researchers acknowledge a massive immediate roadblock. The architecture is sound, the math checks out, but we lack the data required to train it.
The data bottleneck is severe.
To illustrate why current models fail and what kind of data we actually need, the paper highlights this specific puzzle from a benchmark called SimpleBench.
Oh, this is a great example.
I love this one. I want to run this by you, the listener, right now, just to see how your human brain handles it compared to an LLM.
Listen closely.
Okay, imagine a juggler. She throws a solid blue ball 1 meter straight up into the air. Immediately after, she throws a solid purple ball, identical in size, 2 meters into the air.
Okay.
Then she carefully climbs to the very top of a tall ladder while balancing a yellow balloon on her head. The question is, where is the purple ball most likely located right now in relation to the blue ball?
So, as I listen to you describe that, my brain is automatically generating a sequence of events. I am not doing math, I am watching a mental movie.
Right. A human sees the 2-meter throw, knows it takes maybe a second or two to fall back down, and then sees the woman carefully climbing a tall ladder, which is a process that takes significantly longer than 2 seconds.
Much longer.
So the answer is totally obvious. Both balls are resting on the ground. They're at the exact same height.
Yet, if you feed that exact prompt into current state-of-the-art text LLMs, they fail spectacularly.
Wait, really? State-of-the-art?
Yes, because they lack that spatial and temporal anchoring. They process the scenario as a purely symbolic physics equation. They over-formalize the prompt.
What do you mean by over-formalize?
They begin calculating unspecified variables, like the exact launch velocity required for a 2-meter trajectory versus a 1-meter trajectory, or the aerodynamic drag of a solid sphere.
Oh my gosh. They get so lost in the mathematical parameters of the throw that they completely miss the massive temporal discrepancy of the ladder climb.
Exactly. They lack the basic physical intuition that a human accesses instantly just by picturing it.
And this highlights the critical call to action in the paper's epilogue. The AI community desperately needs new data sets to fix this.
We do. Because the problem with existing data sets is their structure.
Right.
A visual question answering data set, like the fridge app you mentioned earlier, it provides the image up front. The visual is the input.
Yeah.
A text-to-video data set asks the AI to generate an image as the final product. The visual is the output.
But to train an Einstein world model, we need data sets where the AI starts with pure text, recognizes its own physical ignorance, decides to generate a visual to bridge the gap, and then translates that visual back into a text-based answer.
Text in, visual reasoning in the middle, text out.
We need benchmarks designed specifically to force an internal visual thought experiment.
And just as importantly, those datasets must include counterexamples where visualization is a total waste of time to reinforce that selectivity training of the GRPO stage we talked about.
Right, to teach it not to build a papier-mâché volcano for a math worksheet.
Exactly.
So, synthesizing all of this, what is the core takeaway for you, the listener, as you look at the landscape of generative AI today? We are standing on the precipice of a massive structural shift.
A paradigm shift, really.
We are moving away from models that simply calculate the most statistically likely next word based on vast oceans of text. We are moving toward models that construct private, visual simulators within their architecture.
AI is learning to rigorously visually test its own assumptions in a hidden sandbox before it ever presents an answer to you.
It's a profound leap toward something resembling synthetic physical intuition.
It is. But, if we extrapolate the trajectory of this architecture, it raises a rather unnerving question about our own cognitive future.
Oh, where are you going with this?
Well, we discussed how EWMs essentially externalize the imagination, right? Turning the napkin sketch into an automated computational process.
Outsourcing the visualization.
Exactly. If future reasoning models can seamlessly generate highly complex, multi-layered visual temporal rollouts to solve abstract problems simulating counterfactual physics and multidimensional geometry far better and faster than the human mind ever could do, we eventually stop doing it ourselves.
Oh, wow.
If an AI can instantly provide the perfect visual thought experiment for any scientific query, do human scientists slowly lose the cognitive muscle required to do what Einstein did at the Bern clock tower in the first place?
That is a terrifying thought.
We might be building a perfect artificial imagination at the exact cost of our own.
Wow. We could be automating the human eureka moment right out of existence. It really makes you wonder what other cognitive muscles we are offloading to these models without even realizing it. Because sometimes having the AI build a napkin sketch for you means you just forget how to draw.